to port 19. This is pretty granular. And that's pretty awesome. So now because of this, if router 1 is blocking this traffic in any direction, we might have a problem. So PC1 sends the traffic out. It's sourced with 19, destined for 50, and I'm denying port 19 at this moment. This command was just to show you that it's possible. And I'm denying port 19. Doesn't matter. If I deny it coming in, when it gets to this point, it'll die. If I drop it from going out, guess what? It'll never leave the router. It'll go into the router, just never leave the router. So once this traffic gets here, 19 is blocked, man. It's not going any farther. And you're going to be looking at PC1 and PC2, and you're just going to be like, I just don't understand. What's going on? Where is it being dropped? You won't be asking where would it be dropped. You would ask yourself, why isn't it working? I'm sorry about that. That's what you're going to be asking yourself. You're going to be looking at PC1, and you're going to be looking at PC2, and you're going to be saying, I don't understand. They're set up correctly, and you're going to keep rebooting, making changes, not understanding what's going on, and the bottom line is it's blocked here. That's why your traffic's not going through. And you're still not going to understand it because you're going to be like, this doesn't make any sense. I ping PC2 from here over to here, and it works fine. It works great. Of course your pings work. But remember, once something pings, everything works. Everything is right. Everything should be working. The number one thing you're going to get as a network engineer, they're going to say, well, Kyle, you're wrong. It's pinging just fine. There's nothing wrong. Oh, really? You're telling me if I have two devices it's pinging, there's nothing else that can be going wrong? That shows me it's getting past the firewall. No, it doesn't. Because what port numbers are you trying to use when you're sending a ping? All that's telling me is the ICMP packets are allowed through the firewall. Doesn't tell me that your traffic, doesn't tell me that because the ping went through that your traffic's going to go through. So you got to be careful with this. So this layer, this information is very important. This source and destination port number, because every device downstream or upstream you need to realize needs to be open, or else along the path your traffic will get blocked, and your routers can look at layer 4. Remember in the beginning I said you probably, it's layer 2 and 3 is where you're going to be spending most of your time, and sometimes layer 4. That's true. But it's more than you think. It's not just, once in a while I'll deal with transport layer. No, you need to understand how these layers are built. Very crucial. Now, even if this is not the case, let's say I don't have anything blocked, 19 or 50. There's no point of doing 50, because if I show you how 19 is being blocked, 50 is going to do the same thing. Even though I said I was going to show you both. But this information finally gets all the way across here, and it comes into PC2. However, PC2 is not accepting the information. Why? Because PC2 is not listening on port 50. Guys, I want you to understand this. How many times you order a pizza and then you realize like an hour's gone by, where the hell's my pizza? You call them up and they were like, sir, we were there. No, you won't. I was upstairs the whole time. No one knocked. Yep, sorry, sir, we were there. Now, did he really show up, or did they happen to knock when you went up to the bathroom and you just didn't hear the door? How can you open up a door if you're not listening to it, if you can't hear it? How can you open up a door when data comes to your door if you don't listen out for it? You can't. How can you answer a telephone ring if you don't hear it? You can't. Okay? So these ports this PC needs to be listening on port 50 in order to receive that information in on port 50. So port numbers are really important to understand in that fashion. You can have port numbers be transmitted with TCP or UDP. You would have the server, let's say this is a server, you would have the server listening on the ports for the services you want to provide. If this is a DNS server, you need to have port 53 open. Otherwise, it's not going to do its job. No one's going to be able to communicate with it. Our source port numbers are obviously the port numbers that come from the person who is sending the data. Because when that information comes over here, let's recap and let's go through this again. Get rid of all this. PC2 is getting this data with this information coming in. When he goes to send the information back over, because this data here is PC asking for a request. This data is going to be him sending back the information that was requested for him. However, when he goes to build his layer 4 information, he's going to be using the information that came from where? PC1. Since it was sourced by 19, obviously he's going to put the destination as 19. And the source is going to be himself, which is going to be source 50. The IP header, what's that going to be? The source IP address is going to be source IP, destination IP. The source IP obviously is going to be PC2, and the source IP is actually going to be PC1. How does he know to send it back to PC1? Because PC1 put it in this information to begin with. He put the source IP address as himself. So when PC2 gets that information over here, he knows that it was sourced from PC1. So obviously when he goes to send the data back, he's going to put PC1's IP address in the destination IP because he wants to get it back to PC1. So these source and port destinations, these source and destination IP addresses and MAC addresses, crucial. Now we have a certain thing called well-known port numbers. They're the first 1,024 port numbers. And how many port numbers do we have available? And I'm going to click here. And let's see what our first 1,024 numbers are. You even see right in here, Wiki, it says well-known port numbers. The first 1,024. That's a lot of port numbers. Notice that we stop at 1,023. And let's go take a look at some of these port numbers. Notice that our port number list says TCP, UDP. If it's blank, it means that it can't be used as TCP in theory, based on the fact that at this moment, this is the way it is. Status means that it's official. That means this is the way it is by the powers that be. You should know that the first 1,024 are well-known port numbers. So some well-known things that you need to understand. Well-known port numbers that you really should know at the top of your head by the time you take your CCNA exam. And pretty much throughout your networking career, you're going to forget, man. It's just very simple. There's times that I've forgotten 23 for Telnet. I'm like, is that 22? I mean, even SSH. I kept calling it SSH 25. I don't know why. It was just something that I did. So FTP, SSH, TFTP, SMTP, DNS, Telnet, HTTP, HTTPS, POP3, DHCP. These are ones that I will commit to memory. I tried to do the TCP and UDP aspect of it. Man, I failed every time. I just took it out. I was just like, forget it. I'm having a hard enough time remembering the port numbers. I'm not going to try to remember if it does TCP and UDP. And that's pretty much with port numbers, man. That's pretty much how they work and how they function. So this whole lesson was really about TCP. The three-way handshake, sequence numbers, and port numbers. And don't forget acknowledgements as well. And remember, we have synchronization and acknowledgements in our three-way handshake, but we also have sequence numbers and acknowledgement numbers in our TCP header. Unfortunately, when you're learning these courses, normally you get confused with those, and usually the instructor is not separating those two. And that's really the bad aspect of it, because you need to understand that three-way handshake is just to guarantee that two-way communication is available. And then the TCP session or the TCP headers will allow that guaranteed delivery to take place. And our data will not go any further until that TCP session has been established. If we're using TCP as a mechanism, as a mechanism of transmitting our data. It's the best way to say it. Okay? So now, communication types. In our layer 3 header, we're going to have a source IP and a destination IP, which you saw me write as SIP and DIP. So our source IP, let's say this is PC, this PC over here, 192.168.1.1, and this one is 200.1.1.1. If the data is originating here at PC1, trying to get over here to PC2, when he's building this layer 3 information, which PC1 is going to be building this information, he's going to have the source IP of 192.168.1.1 because that's his address. So it is being sourced from him. The destination IP address would need to go to 200.1.1.1. So when that traffic leaves here or come over to the router will look at the layer 3 information and say, oh, the destination that you need to go to is 200.1.1.1. That, in order for me to get to 201.1.1.1, I need to send the information out this interface. Hits the switch, come over here to PC2. Now, when PC2 looks at that information and looks at the layer 3 information, remember he's going to look at the layer 2 first, but he looked at the layer 2, he opens it up, and the layer 3 information has a destination of 200.1.1.1. Now he's going to look at that and say, well, that's my IP address, so this belongs to me. When PC2 send data back to PC1, and let's ask the question why. Why would we want to do that? Well, I sent out a request. So this information here to 200.1.1.1.1, I'm requesting information from PC2. PC2 wants to reply to that information. So his layer 3 information is going to be, the source IP is going to be himself, and the destination IP is the information that he received originally from the source. PC1 sent me data. I know it came from PC1 because his IP address is in the source. So when I need to reply to this information for PC1, I'm going to look in the source information in order to find out who sent it to me. So when I know I need to communicate back with him, that's the IP address that I'm going to go to. So therefore, as that's the IP address I need to go to, that's going to be my destination IP address. Just like I was talking about with the letter and the envelopes when you're mailing. But because we have a source and a destination, we're going to one destination. That's it, guys. That's it. It's plain and simple where we're going. We're coming from here and we're going to here. Period. We call this unicast because we have one source and one destination. We're communicating between you and another person. We like to call it unicast because it's only one person. Uni means one. Because from my perspective, I'm only talking to one person. From PC2's perspective, I'm only talking to one person. Hence the concept or the term unicast. We're sending it one-to-one. Broadcast. Now, broadcast is the concept of sending one message to all. In my layer 3 information, this is PC1, 192.168.1.1. He is going to have a source IP of 192.168.1.1, and he's going to have a destination IP of all 255s. Now, when you get to learn subnetting, you'll learn that there's another number we can use. But in this concept, in this concept that we're learning here, all 255s, which means you're saying right here, I am 192.168.1.1, and I'm talking to everyone. Whenever a switch gets a broadcast message, which this is a layer 3 message, not layer 2. If it was a layer 2 broadcast, it would be all Fs. Kind of makes sense, doesn't it? Since we kind of learned a little bit about hexadecimal and how we have 0 through 9 and A through F. And because we learned that, that's kind of the last digit in each one of the numbers, right? In each one of our sets of numbers, the highest number could be is 255. So if we send something to all 255s in every number, it's a broadcast. If each one of our digits are 15, or in our scenario here, or in hexadecimal meaning F, then what does that mean? We're sending it out as broadcast. Now, the reason why I only drew these PCs is because a router, by default, does not forward broadcast messages. It does not. So whenever a router gets a broadcast message, because he will get this message, it stops right there. The router doesn't forward this traffic. There's ways of dealing with that, but at this moment in your CCNA studies, just know that a router does not forward broadcast messages. So that broadcast will get all the way up to this interface, and this will die. Right then and there. So a broadcast message is one to all. So now we can talk about multicast. Multicast is interesting because here we got this PC, and the layer 3 information will be source IP, will be 192.168.1.1, and the destination IP will be a multicast address. Now, multicast addresses start with 224, and you'll learn about that later on. So let's say we have a multicast address of 224